Okay, welcome to our Thinking Beyond, our last Thinking Beyond of this semester and this calendar year. We will start up again in the spring in January, the last Monday of the month per usual at the 6 p.m. Mountain Standard Time. And I will send out all the information on our speaker and the registration links about mid-January. So look out on social media and email for that. So other than that, just tonight, if you have any questions, please use the Q&A feature at the bottom of your screen, and we'll get to those towards the end of the hour. And so that's all I have. So I'll turn it over to the director of the Beyond Center, Paul Davies.
Hello, everybody, and welcome to the fourth in our semester series from Australia. It's my pleasure to introduce today's presenter, Tamara Davis. Now, I've known Tamara since she was a student. She used to come over to our apartment in Sydney, and we talk about black hole entropy and things like that, and we wrote some papers along with Charlie Lineweaver. But whenever I think of Tamara, I think of the movie Sliding Doors. I'm sure you're familiar with it, because there was a point when Tamara might have gone on to a glittering career in sport with her expertise in ultimate frisbee. It was a close run thing as to whether it would be that or theoretical physics and cosmology, and I'm pleased to say she made the right choice, and she has become eminent in the subject of cosmology. And in fact, she leads the Australian Dark Energy Survey. She's also Deputy Director of the Australian Research Council Centre for Excellence for Gravitational Wave Discovery. She was awarded the Order of Australia. She's got a number of other awards. I should say that she's done postdocs at the Australian National University and the University of Copenhagen, but she is now a professor at the University of Queensland. So eminently suited to talk about the subject of today's presentation, which is about dark energy. What is it, and is it changing with time? So I'm not going to say any more, but hand over to you, Tamara, and let's hear what you have to say about this evidence.
Thanks so much, Paul, and hi, everybody. It's an absolute pleasure to be here. Thanks for inviting me along. I was going to talk a little bit about dark energy and some of the latest news on that. I'm not sure exactly who's in the audience, whether we've got a lot of professional cosmologists or a lot of people from different fields. So I'm putting a reasonable amount of some of the details into this talk, but feel free to ask any questions at any time. And Paul will, I think, be watching the chat and relay questions to me if I'm going in at the wrong level for what the audience wants to know. So, firstly, the big picture. So we know now that the universe is behaving in some weird ways. We see evidence that maybe 25% of the energy density of the universe is in some sort of form of dark matter, probably a particle of some sort. We can see that from rotating galaxies, lensing from of light due to gravity, from the cosmic microwave background. All sorts of different pieces of evidence say that there's some sort of dark matter out of there, and it has attractive gravitational pull. For the last 25 years, we've also seen very strong evidence that there's some kind of dark energy out there. That basically, dark energy is the name we give to whatever is accelerating the expansion of the universe. Something's causing the expansion to speed up instead of slow down, as was originally expected due to the gravitational pull of all of the galaxies. That should be slowing it down, but it seems to be speeding up. And ever since the discovery of that in the late 1990s, people have been trying to figure out what is doing the pushing. And that's basically what I've spent my career trying to figure out. So I'm going to be talking about some of the latest evidence we have for this and what we've learned in the last few years about these topics. Now, these are important in terms of understanding what the fate of the universe is going to be. That was actually some of the original motivation for looking into this, in that ever since we've known that the universe was expanding, we wanted to know whether it would recollapse, whether it would sort of coast, whether it would expand forever. And one thing that hadn't really been considered that seriously was whether the expansion was speeding up. Until supernovae in the 1990s showed that the expansion rate in the recent past has been accelerating. And we now know that it seems to have decelerated for the first sort of half the age of the universe and then started to accelerate. And so that means that if this is true, if this is in the case, if, you know, the dark energy is just a sort of a constant background vacuum energy, that's the sort of leading contender, that it's just maybe the energy of the vacuum itself, and as the universe gets more dilute, it has taken over and the acceleration is dominating, and it could accelerate forever. But we want to know whether that's true, whether it really is a constant background acceleration, or whether something more interesting perhaps is going on. Not that that's not interesting enough. So I'll skip the big rip. A few years back, for me, I started this in 2012, but a lot of people had worked on this long before that to design and build a new camera for the CTIO 4-meter telescope down in Chile, called DECCAM, which is this guy on the right here. With that, we did a survey called the Dark Energy Survey, or DES. And we spent many years observing the sky. This is the field of view of DECCAM. You can see there's lots of different CCDs, digital cameras, all sort of tiled together to make a big field of view. And you can fit, I think I don't have it there, but this is to give a sense of scale. You can fit 4 full moons side by side across here. So that's how big the field of view is. And we observed for 6 years and produced a catalogue of over 500 million galaxies. And while there, you know, just sort of accidentally found 700,000 asteroids and tens of thousands of supernovae. We did this survey over this patch of the sky. So this is actually a map that was done using weak lensing. Sort of the sort of pink tanky shape is the region of the sky that DES surveyed. And the bright spots and the dark spots are clusters and voids as seen by the bending of light from background galaxies. So the foreground galaxies warp the shapes of the background galaxies. And this pattern that you're seeing is the inferred density of dark matter in the foreground that we understand from that warping. Now, what I'm going to talk about today, though, is the results from the supernova survey. And with the supernova survey, we observed a few patches of that area, but we also wanted to get spectra. So with DES, you just get images, so you get pictures, and we had 5 different colors for most of it, 4 different colors for some of it, so different pass bands. But for a few of the regions, we repeatedly went back to those regions, and here what you're looking at is the 2DF robot, so the 2-degree field robot. And what you're seeing is this robot is putting optical fibers at the positions of interesting galaxies that we want to take spectra of. So that this is going to flip around and face the mirror. The mirror is down at the bottom there. And we're going to capture the light from each individual galaxy of interest in one optical fiber and get a spectrum of that galaxy. So this has 400 optical fibers, and with that we can get almost 400 galaxies at a time and measure their spectra. So it's a really efficient way to follow up the images that we get from DES. It just so happens that the images we get from DECCAM over in Chile and the field of view of 2DF are exactly the same. So it's a very efficient way to follow up images from DECCAM. So here's some of the team that was in the supernova part of the Dark Energy Survey. And there's many more involved in DES. We have about 500 people in the collaboration, but here's a few of the people whose work I'll be talking about. And lots of the work that I'm about to talk about was done by the early career researchers, the PhD students and postdocs that were part of this team. And I'll try and point out some of them as we go along. These little circles here, the blue and red little circles, are the regions that we follow. There's 10 pointings in 4 clusters. And these were the regions we went back to weekly in order to discover exploding stars. So we wanted to find things that changed. So we basically took images in these regions and looked and saw each week what changed, and then tracked the brightness of those variable objects over time. So we did about weekly cadence for imaging and about monthly cadence for spectroscopy, and measured the spectra of these objects. And here, or not necessarily of the objects, of the host galaxies of the objects. So here is my sort of a fun visualization of our data. We're sitting at the center here on Earth, and the yellow dots are the positions of galaxies in the fields that we're looking at, those sort of 4 regions. And where the intensity drops off, sort of about there, if you can see my mouse, the intensity drops off, that's at a redshift of 1, which means the light from there has been traveling for about half the age of the universe. So these are really long, thin pencil beams. And the sparkles that you see going off, those are the positions of supernovae and the timings of supernovae that went off during the first few years of our survey. And you see it goes dull and there's no sparkles for a little while. That's the 6-month break that we had while these fields go behind the sun, so we can't observe them. Cool. So we observed for 5 years for the supernova part of the survey, and we tried to discover distant supernovae. Now, this histogram that you see here is the number of supernovae as a function of redshift, and the grey histogram in the background is the Pantheon plus compilation, which was until DES came around, was the gold standard for several years, which combines 17 different supernova surveys, basically all of the high quality supernova data that had been collected historically. Now, DES contributed new supernovae following this blue histogram. So you can see this is a real step change in the amount of data that we have at high redshift, so that's far away. And it contributed 80% of the known high quality supernovae above a redshift 0.5. So it's a really fantastic new sample. And there's about 1,500 type 1a supernovae that we contributed that are new from this survey. And again, feel free to stop me if there's any questions. Now, you'll note that our method of looking through these long pencil beams means you're looking really far away, and there's not many supernovae that you're going to catch nearby. So we needed to combine that with a low redshift sample, and that's what we see in the red histogram here. We rejected some of the low redshift ones because their calibrations weren't good enough for our quality control. And so we just took the best quality ones so that we could have the best control of our understanding of the data. So here is what the data looks like. Here's our light curves. So you have, this is 4 different colors, so different passbands, different filters on the telescope. And this is the data for them, rising and fading over time, so the supernovae. So I think this is a fun visualization. I've just offset the data by the redshift. So this vertical axis is where the line hits the vertical axis, is the redshift of the supernova. And you can see that we lose the sort of greener, bluer bands as things get to higher redshift because their light is being pushed towards the red. Okay, so with all that, we make a Hubble diagram. And on the vertical axis, we measure how bright the supernova is. So we take some measure of the peak brightness of the supernova. And on the horizontal axis, we use the spectrum and measure its redshift. And this is what gives us the information about cosmology that we need to test what dark energy and dark matter are doing. So before I go on to some of the cool results, are there any questions so far?
Tamara, I should ask you to define a type 1a supernova for those people that have heard of supernovae but may not know what a type 1a is. So that's critical, isn't it?
Awesome, thanks, Paul. Yeah, so the supernovae come in various types. Some are just single stars that explode at the end of their life. Type 1As, we believe, are white dwarfs, where they gain material from some other star or some other source, and then explode. And so it's like a double star system usually, and there's a particular sort of critical point beyond which a white dwarf star, which is sort of like a dead star, can't hold itself up against the pressure anymore. So if you add more mass to it, it goes, and explodes. And so it's that sort of critical tipping point, which means that type 1As always explode to approximately the same brightness. And we can calibrate that peak brightness, and that means they're standard candles. So we can use them as standard candles, which means we know how intrinsically bright they are. So by measuring how bright they appear, we can tell how far they are away. And that's basically what this is on the vertical axis is. It's a measure of how bright the supernova is, which tells us its distance from us. So it's the distance is on the vertical axis here, and the redshift indicates something about the speed of the galaxy moving away, so about the expansion. And how that expansion changes over time is the thing that tells us how much the universe is accelerating or decelerating. And because we're looking back into the past with these, as we look further and further away, we're seeing the universe as it was in the past, we are able to sort of see effectively how fast the universe was expanding in the past, compare it to how fast it is expanding today, and that tells us about whether it's been accelerating, decelerating, etc.
Well, one other thing, what are the units on that vertical axis?
This is the log of the flux, basically. So this is dimensionless. It's a relative number, and so for the supernovae, we actually don't care what the number is on this axis for this purpose here, for measuring cosmology. We can scale it up and down, whatever. It's a sort of an arbitrary number up here.
Right, we won't worry about it then.
Yeah, so all that matters is how different the number is as a function of redshift, not what the number itself is.
Okay.
Yeah. Cool. Thanks very much. So before I go into the cosmology results in dark energy, I thought I'd do a couple of the fun results that we got to get out of this. And the first fun result is time dilation. So here is that plot I showed before of the supernova light curves. And these are, however, after I've corrected for time dilation. So basically you expect, because the galaxies that are further away are moving away faster, you expect time dilation to occur, and the functional form should be a factor of 1 plus the redshift. So it should be time dilated as a function of time. So these are all divided on the time axis in the bottom here by 1 plus the redshift. Now we went and had a look at measuring the actual time dilation, this 1 plus z effect, and and to do that you had to take into account 1 subtlety. So you can see the light curves that I've highlighted at the bottom here are all the same supernova, and you can see in red colors the light curve shape is different to the light curve shape in blue colors. So if we want to measure how wide the light curves are as a function of redshift, you have to compare the same colors. So you have to choose the pieces of the light curve that the redshifts that have that are sampling the same rest frame part of the light curve. So the light is getting redder, and so you have to sort of find the redshift at which you're sampling the same intrinsic color, and then see if the light curves are wider. And so this is what it looks like when I do not correct for time dilation. And you might not have been able to see that flick very much. So let me flick through it again. This is with after correcting for time dilation, and look at the reddest panel and see how it gets wider as I touch this here. And you can see without correcting for time dilation, the light curves are clearly wider. Now, Ryan Waite, one of my students, went and had a look at this. He picked the samples that are in the same color, and here you can see these sort of light curves. What he's done is just stacked all of the supernovae that we have at these approximate redshifts. And so the closer redshifts ones are orange, and they tend to be narrower than the purple ones, which are at a higher redshift. And if you correct for that stretching, you get them all piled on top of each other, like in the bottom panel. And if you plot the light curve width as a function of redshift, this is the plot that you get, which is absolutely beautiful measurement of time dilation. The theoretical prediction is the dotted black line, and if you can't see the dotted black line, that's because it's under the best fit of the blue dashed line. And so this is just a really fun, pretty measurement of time dilation, which a sort of classic prediction of our expanding model of the universe, but has never been measured to anywhere near this precision before. So that was pretty cool. Another cool thing that we did with the data before I get to the dark energy results is looked at gravitational lensing, because you do actually expect, as light travels through the universe, it gets focused and defocused as it passes by different masses. And when you look at this Hubble diagram, you actually see there's like scatter about the mean. If you looked at this bottom panel, we've subtracted the best fit out, and you see that there's some scatter here, but some of that noise is actually signal, because some of that is focusing of light due to lensing and defocusing. But the problem is that focusing is only a couple of percent, and it's basically an order of magnitude lower than the amount of scatter due to the diversity in supernovae, because they're not perfect standard candles. Nevertheless, we went and looked for it, and this was the first sample that we could get a significant detection of this, because we had such a high redshift sample and the signal increases with redshift, and we had so many supernovae. So Paul went and looked at this. He correlated the magnitude of the supernovae with the expected magnification due to the galaxies that we could see close to it on the line of sight. And when you did this, you get this really messy looking blobs, where what you have on the vertical axis here is how far offset you are from the Hubble diagram, and how much you predicted lensing would be due to the foreground galaxies. Now, if you squint and tilt your head sideways, you might see the expected signal is that there should be a slight trend in this direction, which is a bit, maybe it's not very obvious, but remember, we expect the noise to be 10 times bigger than the signal in this data. And this actually, it turns out that this trend in this direction is the first detection of weak lensing magnification of supernovae at high significance for the first time. So that was just another cool thing. But anyway, onto the gory details of the actual or the fun details of the dark energy part. I'm not going to go into the supernova analysis details, but I'm just going to flash up a couple of things that are the cool additional new stuff that we did that made our supernova dataset so good. We did forward modeling of the photometry, so we did really, really careful calibration of the photometry. We took into account different effects of the atmosphere on the visibility and the seeing of our objects with different colors. We did new light curve fitting. We validated our uncertainties and our assumptions. We checked whether we had the right host galaxies. We did machine learning classification of the supernova light curves. We thought this might be a limitation, but it turns out it was really very clean. We did simulations of our data set so we could take into account biases. And one of the big ones is modeling color, dust, and the intrinsic sort of population of how supernovae behave. So I just skipped over, a dozen, 24 PhD projects in about 30 seconds there. But this is basically where all the effort went in order to get the results that I'm about to show. And so just to give you what we're trying to do here, this is the original plot from Rees and Perlmutter from 98 and 99. This is a combined plot of their data showing the magnitude or the distance modulus as a function of redshift. And this is the original discovery of dark energy. Now, there's a few different models that have been plotted on here. And these models are here. This one here is one that has a matter density of 0.3 of the critical density, which is what observers in the 1990s had been saying the matter density of the universe should be. The dashed line down here that I've made blue is what would be needed to have a matter-only flat universe. And now a flat universe is the thing that theorists had been predicting, and later the cosmic microwave background would also require. And there'd been a big discrepancy between the observers and the theorists here of what that the matter density of the universe should be. But there was a model in which everyone would be happy. And that would be if there was some sort of dark energy that made up the missing gap that between a matter density of 0.3 and a total density of 1, which is what the theorists required. And so this is the curve that would make everybody happy. And this, just if you're looking at how to read a plot like this, the contours are like a bullseye, where the central contour is the region of this parameter space that the data prefer. And so lo and behold, the model that the data really preferred was the one in which everyone was happy, and there was a 0.3 matter density, and the rest of the density needed to make the universe flat was made up of a cosmological constant, which is the simplest form of dark energy, one in which the dark energy is simply a constant. Is that clear to start, Paul?
You should just explain that when you say the universe is flat, you don't mean it's squashed like a pancake. That you mean that in 3 dimensions, the space-time, the spatial curvature is 0. And you floated the term critical density. Maybe you should just say a few words about that.
Wonderful, thanks. Yeah, so flat simply means that the angles of triangles add up to 180 degrees. So you can go anywhere in the universe and measure triangles, and on average, the angles of those triangles will add up to 180 degrees. If the universe is curved, like if you're on the surface of the Earth, you could have angles of triangles not adding up to 180 degrees. And like if you walk from the equator to the North Pole, back down to the equator, and back to or chuck a 90-degree turn at the North Pole, walk to the equator and back, you've done 3 90-degree turns. So you've drawn out a triangle that's 270 degrees. Whereas when we say flat, just technically the 3-dimensional space is flat, triangles add up to 180 degrees. The critical density is the density needed to make the universe flat. If you were higher density than that, then you would have light beams converging, parallel lines would not stay straight, and you'd have angles of triangles being bigger than 180 degrees, and vice versa for open. So hopefully that clears up some of that. Okay, so let's get to the DES results. So here you have the same plot that we had before, where you've got the cosmological constant on the vertical axis and the matter density, and we've got that sort of bullseye sort of plot. The blue one here is what you get from the supernovae alone. And so it's similar to the plot that we had here just a second ago. You can see it's like in the same degeneracy direction, and almost depressingly similar, to be honest. But you can do a comparison where you have this, and you have a look at where we are with modern data 25 years later, and they look similar until you change the axis and scale it to the correct scale. So this is how much we've been able to zoom in on the best fit parameters compared to what was in the late 1990s. So we have come at least a little bit of a ways there. Now, we combined with some other results in our paper with measurements of the large-scale structure of the universe, with measurements from the cosmic microwave background, and by something called the 2 by 3 point correlations, which I won't go into in any great detail. It's just that what you do is you measure correlations between different features of the universe. You measure the positions of galaxies compared to where the other galaxies are. You measure the positions of galaxies compared to the shapes of background galaxies, and this is where you measure lensing. And you compare the lenses compared to the lenses, and you combine all of this data together, and that gives you a measure of the cosmology. So I don't have time to go into that in great detail, but that's the other thing that we added. And so you can see here the sort of light orange or yellow curve is when we combine with the large-scale structure, baryon acoustic oscillations, and 3.2 point, and the blue is when we combine with CMB, and the darker orange is when we combine with all of them. And so this is like you can see that the cosmic microwave background alone has this big degeneracy, supernova alone have this big degeneracy, and BAO alone have this big degeneracy, which I haven't shown here, but when you put them all together, they all cross at sort of like an X marks the spot sort of point, and that's our best parameters within this model of the universe. But this model of the universe is one in which dark energy is a constant. And we want to know whether that's actually true or not. So we want to allow some flexibility and see if there's any evidence that dark energy behaves like not a cosmological constant. And the standard way to first do that is just to look if the equation of state, so the equation of state is how something the pressure relates to the density and how that changes as the universe evolves. Now, if it's a constant, then W is -1 exactly. And so here you can see in blue again the best fit from supernovae, which is a bit above the W equals -1 line. Not a huge amount. This is like it's about a 2 sigma deviation, if you like sigmas. And that's when you combine with the CMB and the BAO and the 3x2 point, you also end up with about a 2 sigma deviation from the standard model. Now, no one gets too excited about 2 sigma deviations. They happen as statistical fluctuations, 1 in 20 times type of thing. And often cosmologists have been known to underestimate their error bars, although we have tried really hard not to do that. But it's a 2 sigma result, but nevertheless, it's sort of a little bit tantalizing. And I should say that there was another set of supernovae that were released just a month before the DES ones were, and that's Union 3, which is sort of like Pantheon Plus. It was a big conglomeration of many other supernova, and they find the same thing as our new data, just with slightly bigger error bars, but they also find W a little bit above -1 in this data set. Now, this one's super complicated. Sorry about this plot, but we wanted to do one last test, which is to see whether there's any evidence that dark energy could vary with time. So previously that was testing for a constant equation of state, but now we're looking for whether that equation of state could change with time. And this complicated looking plot, basically the dotted lines again are the standard model in which W is equal to -1 and there's no changing with time. WA would be equal to 0 if there's no changing with time. And you can see that the best fit of the supernovae doesn't lie. The bullseye is not on the crosshairs. And if you zoom in, you can see even combining with other data, we're a little bit off. Again, it's about a 2 sigma result, so we're not saying that this is a massive discovery of time variation. It's just saying that there's hints that dark energy might be more complicated than just a constant equation of state W equals -1. Now, this was the complicated part of things, probably. And so I should ask if there's any questions. I've got a little bit more to show, but is there any questions at this point?
Yeah, well, just a comment that what you're showing is that the dark energy, there's a hint that it's getting weaker with time. You haven't said whether it's getting weaker or stronger, but it's getting
Thank
weaker.
you. Yes. So this would be that dark energy was weakening with time. So it was stronger in the past and getting weaker. So that means that talking about, fate of the universe, it might be that if it's definitely accelerating forever, and dark energy is the same strength, then it definitely would expand forever. If it weakens, we could be in a situation where if it weakens so much that it turns around and becomes attractive, we really don't have any idea what happens at the moment, or what would happen. But if it does become attractive, the universe could still recollapse. So that's like a big deal for the fate of the universe. But more interestingly, it's a deal for what the fundamental physics is that's causing this acceleration in the first place. Now, this model that I fit for is just a linear model. So it's like basically a Taylor expansion, a first order expansion, looking for whether there's any hint. It's not a physical model that anyone expects to be true out to all scale factors into the infinite past and into the infinite future. It's just looking that whether, if we give the model more flexibility, whether the data suggests that that's required. So that's sort of as much as we should be really reading into this, but the data does seem to suggest maybe it's weakening just a little bit. And we tested a whole bunch of different models. This plot I was never going to explain in any detail, but basically, if you add more flexibility to the models, then most of the different types of flexibility we added to a whole bunch of different exotic models that we tested mean that those models are slightly preferred or moderately preferred over the standard cosmological model. So that was some of Ryan's work. Yeah, so if you want to do this, the DES data are all public. You can go and play with it yourself, and we've given some tutorials and some code that you can go and play with. So go and download these yourselves. But before signing off, I wanted to show one last piece of data from a different survey. Do I have time for that, Paul?
Yes, do go ahead.
Excellent. So, because the dark energy spectroscopic instrument is another one that I've been working with, which is a fantastic, spectacular instrument. Remember, I showed you the video of the 400 optical fibers at once on the telescope in Australia that we were using to follow up DES? Well, this is 5,000 optical fibers. And instead of having one robot for each of them, each fiber has its own robot. And they can each configure simultaneously. So rather than taking like 40 minutes to configure a field, which is what the previous one I showed does, this one can reconfigure in just a couple of minutes, which means it's an incredibly efficient machine for following up and doing surveys of the redshifts of galaxies. So with this, DESI has been mapping the sky, and there's this cool video actually, which you can go and zoom in and on some of these. This is from a planetarium show that DESI made, and you can go and have a look at how it all works. But DESI so the stuff I was showing from DES was released in January, and DESI in April put out their first year of data measurements using the structure of the sort of bubbles or voids in the distribution of galaxies as a sort of a ruler, like grid paper, to measure how the expansion of the universe has changed over time. And this is a really strong way to measure the expansion. And DESI found a similar result to DES. So here you have the WA W0 panel. So this is time variation on the vertical axis and the present day value on the horizontal. And DES was finding that it preferred the bottom right quadrant of this compared to where the standard model is. And DESI finds the same thing. So this is a completely different type of measurement, but finding time variation in the same direction. Now, DESI is by itself maybe a tiny bit weaker than the DES measurement, but they're very, very similar in that the strength of indication for any time variation. But put them together and it starts to get interesting. You start to get a more significant than 2 sigma result. And so this everyone went crazy about this, and everyone got very excited about this potential result to see whether this is true. But note that they're not at the same angle exactly. So there's a lot of work to be done to improve both of these measurements and get more information before we jump to any conclusions about time variation. I'm going to skip this unless anybody asks, and say that there's also other cool things that you can do with this data, like measure H0 by making an inverse distance ladder. I think I'll skip over this for time, but if anyone has any...
What do you mean by H0?
Okay, yeah. Sorry, going a bit too fast. Thanks, Paul. H0 is the Hubble parameter, or the Hubble constant, which is the rate of expansion of the universe at the present day. And it's a slightly controversial number at the moment because measurements of the cosmic microwave background and some other large-scale structure measurements are saying that it should be in the high 60s, like 67, 68 kilometers per second for every megaparsec of the universe. But measurements directly of measuring the expansion nearby using Cepheid variables and other types of calibrators at low redshift tend to indicate slightly higher measurements, so 72, 73-ish. And there's controversy on both sides because the error bars on these are now small enough that they disagree somewhat significantly. So measuring this in a different way is particularly interesting. So what we did was, with the supernovae that we had, we calibrated them using the large-scale structure. So using the measurements not from DESI, but from previous large-scale structure measurements from SDSS, and used them to calibrate instead of using Cepheid variables. So it's the distance ladder is usually you go from geometry, like parallax, to calibrate how bright Cepheid variables are, and then you use Cepheids to calibrate how bright type 1a supernovae are, and then you use them to measure Hubble constant. So we do it the other way around, starting from very, very far away things using cosmic microwave background, calibrate sound horizon scales, and use them to calibrate the supernovae at high redshift and see what that implies for the low redshift, the nearby expansion rate. And when you do this, you get an H0 that's in the that agrees with the CMB, which is not surprising because you've calibrated to that value. All this it really says is the expansion history doesn't vary so dramatically at low redshift that you can get a measurement of 73 kilometers per second per megaparsec. Sorry, the intercept here gives you the value of H naught. So there's no massive, the supernovae show there's no weird evolution going on at low redshift that could explain the discrepancy. So that was a bit of a technical one as well. So I just wanted to conclude by saying that I showed you this zoom in before of where the DES supernova stuff is. That this is a prediction of how good DESI will be when its final data are out. And this is zoom in on there. So if you can barely see that little dot here, that the final DESI measurements after 5 or more years of observing are going to be phenomenal, and hopefully will resolve some of this question about whether the time variation in dark energy is real or just a statistical fluctuation at the moment. And so there's a whole bunch more stuff to do. Here's a few of the papers that you might want to look up if you're interested to see any of these things. But I'll turn over for questions, and thanks very much.
Thank you, Tamara. Before we leave your final remarks, just for my own clarification, the measurement of the Hubble constant H naught, you mentioned that there was a tension, the Hubble tension, between two different methods of measuring it. And I thought you were going to say, well, our data resolves the Hubble tension, and here's the definitive answer, and it's somewhere in between the two. But what you said, I think, is that you have confirmed there is a tension. You haven't resolved it.
Definitely have not resolved it. No, all we did was we used BAO, so baryon acoustic oscillations in the CMB, to calibrate the brightness of supernovae. And when you use those to calibrate the brightness of supernovae, you get an H naught that's consistent with BAO and CMB, which is as you expect because you've used those as your calibrator. What I think the most interesting thing this plot shows is basically what this has done is remember how I said we could move the supernovae up and down before because it was an arbitrary axis because we hadn't calibrated the absolute magnitude. So the number on that vertical axis doesn't matter. The baryon acoustic oscillations, which are the red data points in this plot, are calibrated, and so they tell you the distance to this redshift. So what we've basically done is shifted the supernovae so that they agree with the BAO, and then you can see where you do a best fit and where this hits this axis is what the measurement of H naught would need to be consistent with that. And yeah, you can see that this hits this axis in the 60s, not up in the 70s. And so that's saying that there's nothing dramatic happening with the shape of the expansion between the BAO measurements and redshift 0 that would allow us to change that, that would help us resolve that tension. So it's saying that the tension remains there. Yeah.
And that just picks up on one of the questions that we've received, which is about the question I was asked is I've heard that there's a problem where different methods of measuring dark energy yield different results. I think that a question is maybe confusing that with the Hubble tension we've just been talking about. In other words, different methods of measuring the expansion of the universe. But I may be wrong. Are there different methods of measuring dark energy that don't agree?
Well, you can see I'll flick back a little bit. So to some of these, like these kind of plots here. So on this, at least, you can see the supernovae are the blue, and the cosmic microwave background is the black dashed line here. And so if you wanted to take the best fit of these, it's in the sort of the center of these black dash contours would be the CMB, and the center of these blue contours would be the supernovae. But the error bars on these are large, right? Like you can see the size of this contour is big. So basically this is saying that anywhere within these this blue area is a reasonable fit to the supernova data. And similarly, anywhere within this black dashed line is a reasonable fit to the CMB. So they do overlap, and they don't overlap right in the middle, but that's expected statistically. You would only expect them to overlap right in the middle if you were really lucky and just happened to get the correct answer for both from your statistical fluctuations. So you can see these, and they're not massively discrepant here. And similarly, they don't necessarily overlap at the 1 sigma region, but they do overlap in these other parameter spaces. So we did test whether it was okay to combine all of these, whether they were consistent enough, and statistically they're all consistent. All of these different probes that we added here were consistent to measure dark energy with, and so we were technically allowed to combine them. So we did check for that. Now there's a variety of different things for cosmology that are causing problems at the moment, though. So we've already mentioned that H0 measurements are inconsistent, so you can't combine the usual, like the low redshift calibrated supernova measurements with CMB measurements and get an average and find out what that is, because they really are too far away to be consistent to do that. So there's inconsistencies in H0. There's also hints of inconsistencies in a different parameter that I didn't show here, which is not a measure of the expansion, but rather a measure of the clustering within that expansion. So measuring how dense and underdense regions are, there's a parameter called sigma 8, which tells you what the sort of average clustering is at a scale of H inverse megaparsecs. And that number appears to be slightly inconsistent between measurements of lensing and measurements from the CMB, for example. And that's, again, that one's not as bad a discrepancy as the H0, but it keeps people up at night a little bit. And the other thing that I would say is that there's measurements of bulk flows, measurements of motion in the universe, tend to find motions that are too big compared to what's predicted from lambda CDM. Again, it's not as big a discrepancy as H0, but it's something that people are actively looking at to see if there's anything weird going on there. So I think what the situation we're in at the moment is cumulatively there's a whole bunch of little niggly things that anyone alone wouldn't challenge the model too much, but we put them all together. It can be either we're being over optimistic on our error bars and we're just missing something in our analysis, or there's a more complex model underlying it that would simultaneously explain all of these slight discrepancies. So you'll find people in both camps, and we just need to keep working, get better data, and keep improving our theory so that we understand exactly what's going on and see whether we've stuffed up our measurements in any subtle way, or whether it's there's sort of some true things that needs cool new theory to explain.
Okay, we've got some more questions, but I'd like to ask Sara if she wants to pitch in on this discussion.
It was actually a good lead off into my question, because I'm always interested in sort of the underlying explanations for the data. So I'm wondering about some of the theories that might be coming online that like you're testing or thinking about, and what that space looks like right now, or if people are just migrating into that space to try to explain the data before it's, yeah.
Yeah, no, I have I don't have that slide in this particular slide deck, but I made a slide of all of the possible sort of ideas for what dark energy could be that people have proposed. And I just like going through 6 months of papers in the literature, and you just have a page where you just scroll down all of the different possibilities that people have proposed. So the paper that Ryan had here's a whole bunch of different ones. These are not necessarily the most favorite ones to look into, but there's like, this is thawing dark energy where it gets weaker, and some of these are not that well motivated, but there's kind of things like, one of the leading ones is early dark energy, whether there was some dark energy that was bigger than expected early on in the universe. And there's other things like actually maybe some of the inhomogeneities in the universe are biasing our views. That's actually one of my favorites, is to understand whether the local universe, the universe close to us, is biasing, because we've got things like there's this structure in when we're measuring the expansion, we're assuming that it's homogeneous, but it's possible that there's structures that are biasing what we're seeing. In particular, every photon that we see moves through our local universe, the universe that's nearby us. So if there's any structures there that are warping our view of the universe beyond, that could have an effect. So there's everything from differences in large-scale structure that we haven't taken into account to fundamental differences of how the vacuum or dark energy would behave that are possibilities here.
Sarah, do you have anything more to add, or can I pick up on
No,
one
there's
of
a
the
lot of questions in the chat that maybe we should get to some more.
Right. There's one that I think we can deal with fairly quickly, which is somebody's asking whether, when we talk about the expansion of the universe, the space within galaxies is expanding, and I think I can confidently say no, that's not what we mean. It's the space between the galaxies, and in fact between clusters of galaxies, that systems which are gravitationally bound are not partaking in the expansion of the universe. So I hope that clarifies that. And then we have a question from Selden Prairie about the second derivative in the Hubble plot, the change of the Hubble constant. It's not constant, of course, over time. And can we be measuring that, and when are we going to get precise values of that? But actually, isn't that what you've been talking about already?
Yes.
That is precisely those changes.
Yeah. So we're measuring that. We're measuring the acceleration and deceleration of the universe. So that's that is exactly the thing that we're trying to measure, or that we have been measuring here.
Now, Barbara Temple is worried about the end of the universe. I think we're all worried about that. And you did, in passing, say that predictions for the final state of the universe will depend on whether dark energy is constant, or whether it's going to get bigger or smaller, or become negative, something of that sort. Do you want to just say a little bit more about, in the far future, how our poor universe is going to meet its demise?
Yeah, well, that's it's sort of related to how what I started with, that it might like we weren't sure 25 years ago, we really weren't sure whether it was going to recollapse or expand forever. Until any hint of time varying dark energy, we were very confident that it is going to expand forever and just get colder and colder and end up in what's known as the big freeze, where and actually there's a really interesting thing that I think about this, in that in the like distant future, it's going to be quite hard for us to, if we were born then and hadn't seen anything before, it would be quite difficult for us to know that we were in an expanding universe, because all of the galaxies that are moving away from us would have moved so far and accelerated away such that the light from them would never reach us. And so we wouldn't be able to see them anymore. They'd fade from view. And so we would just look like our little cluster of galaxies, and we wouldn't see all of those other ones. And that always makes me think about, if that's the situation for us in the distant future, what are we missing right now because of our time and place in the universe that we don't understand about the universe around us? But anyway, that's a side point. If dark energy were to increase with time, if you had an equation of state that was more negative, then you could end up in something called the Big Rip, where the acceleration of the universe became so extreme and so close that it ripped apart even atoms. I think there's good theoretical reasons to think that that's probably not going to happen, but it's the kind of thing that we do speculate about.
Now, you've mentioned theoretical reasons. You've been talking about these amazing observations and this huge team of people getting more and more precise, and they'll be better in the future. But you must lie awake at night thinking, well, what would explain this time variation? What is this dark energy if it's not just the constant energy of the vacuum of empty space? Do you have any ideas? Do you have a favorite theory as to what's going on here?
Well, I was getting more, and a year ago I was still very convinced that we were probably living in a universe where dark energy was just a cosmological constant. So it was probably just some form of vacuum energy. Now, in quantum physics, there's a prediction that the energy of the vacuum itself, empty space, wouldn't actually be empty, that it would actually have some sort of repulsive force. But the amount that is predicted by quantum physics is way larger than the amount that we observe. So people were like, oh, it probably cancels to zero for some reason that we don't fully understand. But I'm very interested still whether it's some aspect that you can relate to that really fundamental sort of quantum structure of reality, the quantum structure of the vacuum, that would cause dark energy in the first place. And maybe there's some quantized space-time or something like that that explains why it takes the value it does. But maybe that also explains why there would be some subtle evolution in it as the density of the universe changes. I don't have a good solid answer, but I don't think anybody has a good solid answer, because I feel the thing that's lacking at the moment is that aha moment where someone comes up with a theory and everyone's like, oh, yeah, that's so obvious that clearly is how it must be happening. And at the moment, there's a huge number of theories bouncing around about what it could possibly be, but none really have that, for me at least, have that grain of truth where you see it and you're like, ah, yes, that feels right. I know you don't do science by feel, but like when general relativity came around, there was a good philosophical reason to trust it, in that if you wanted all observers to see the same outcomes for experiments, and if light travels at a constant speed, then general relativity follows, basically. So all the theories we have at the moment sort of lack that sort of nice conceptual reason why they would exist. And
I mean, related to that, so Barbara Temple is also asking that this time variation, if it exists, may not be monotonic. It could oscillate. In other words, we could be going through, a few billion years, it gets weaker, gets stronger again. Could be any number of different behaviors. I guess we want the simplest thing always, but do you what do you say to that? The possibility that it may oscillate.
Yes, so I think that's related to what I said earlier, in that this linear approximation is just like looking over a range of scales where we can see where we've made measurements and seen that it seems to be smoothly varying there. But we also would be insensitive to small variations over that time. If it was wiggling around a mean during that time, we still would not be sensitive to that. But until we have a fundamental theory for how this is working and what is causing it, I think it's impossible to predict what will happen in the future. And so if it is completely possible that it would be some oscillating feature.
Okay, we're sort of running out of time, but I'd just like to get in with a very mundane sort of question, because whenever I see all this amazing technology, and I loved your slides and the video clips and so on, and I think it's just incredible how it all works, and you gather this data and can make sense of it. Well, what happens with something as simple as a satellite going overhead? That's going to mess up all the data, isn't it? Or a plane, for that matter. How do you factor out those things?
So for DES in particular, when you're taking big images of the sky, that's a problem. So you don't look anywhere near the horizon at sunrise or sunset, because that's when the satellites are reflecting most. You want to look up where the satellites are hidden behind the shadow of the Earth. But as more and more satellites get up there, it becomes a real problem, and not only for optical astronomy, but also for the radio interference for radio astronomy. And so we'll be looking through a bit of a cloud that we have to subtract those from our data. Otherwise, we're going to get a biased view of the universe. Yeah, so that can be a problem.
All right. Okay, well, Sara, unless you've got any last final comments, we're up against the hour, and I think it's dinner time here. It's probably breakfast time for you, isn't it, Tamara? I can't remember what the time is. Maybe lunchtime. Yeah. But we're really grateful that you've shared these important new results with us. And somebody's asked, could we put the web links and so on in the chat channel? I don't even know how to do that, but presumably anyone interested in following up on this can just contact you directly. And I'm sure you're easy to find. And so I'll just leave it at that. So just remains for me to thank all of the people in the audience, and remember, we'll be back in the new year with another lot of Thinking Beyond. But for today, thank you very much for attending, and thank you once again, Tamara, for giving such a splendid presentation, very thought-provoking. So I'm going to say goodbye, and see you all next year.
Bye.
Thanks for having me.